have this posted later. Okay, so today we're going to talk about graphing. All right, and so you have your handouts with you. What I usually do with my class when we do this is they have their handouts and we just read the handout out loud. And the way I had it set up is uh, throughout the document there's a lot of questions that need to be answered. So we're just going to go through those questions. And so let's get started. So graphing and linear regression. The things you're expected to learn from this activity are, number one, you need to be able to create graphs that effectively convey experimental data. Okay. And this link right here to a YouTube video, I suggest you watch this after class or when you get home because you can get to this at your school. So watch it up to the 17-minute mark. Okay, so that just discusses the kinds of things that are expected in a graph, a typical XY graph that we're going to be talking about today. Okay, what we're going to focus today is graphing things that are linear. So we're going to identify quantities that are linearly related based on the equation that relates them. And we're going to demonstrate linear relationships by creating an Excel chart. So we're going to learn how to create a chart using Excel. We're going to learn how to draw a trend line over the data. So you'd have an Excel chart that might look like this. And then you learn how to overlay a trend line, what's called a linear trend line, also known as the best fit line. So this linear trend line, this is also known as a best fit line. And you're going to determine the slope and the intercept of the line. So the slope, if you remember from your algebra, is just what? A slope is just rise over run, right? So if you have slope, you calculate it using the rise divided by the run. And where it crosses your y-axis, okay, y-axis is the vertical axis, the x-axis is the horizontal axis. So when x is 0, where it crosses the y-axis, that's your y-intercept. Okay. So let's continue. Activity 2. Let's talk about linearly related quantities. We say that two quantities are linearly related, okay? Let's say x and y. They're linearly related if you can obtain one by simply multiplying the other by a constant and then adding another constant. So for example, here in this equation, if I have a variable x, if I multiply that by a constant, which I'm going to call m, and then add another constant, which I'm going to call b, and I get the value for y, then we say that if I were to plot y versus x, I'm going to get a straight line. And the slope of that line, the value of the rise over the run, is going to be whatever this m is, this number that's in front of the x, the coefficient of x, you say. And the y-intercept would be whatever this b is. Okay, so your y-intercept is b. So let's look at a couple of equations and see what the what we need to plot in order to get a straight line. So here's an equation right here that relates might relate the concentration of a reactant versus time. So C, let's say, is concentration, T is time. Okay, so C is equal to negative KT plus C naught. So let's pretend here that C and T are your variables. Okay, you'll notice that if I were to plot C versus T, okay, I should get a straight line. So if my y is C and my x is time, T, you can see that I can get C by multiplying T by negative K. So the slope I expect to see would be negative K. And then, so I can identify C as my y, my T as my x, negative K as my m. So here I can also identify C0 or C naught. Usually when you have a subscript 0, you say not. So C naught is C sub 0. And C naught is going to be my y-intercept. Okay? So let's try this other equation right here. This might be an this would be an equation you would use for, let's say, if you were to measure the volume, the mass of volume and masses of, let's say, water. And you can remember the formula for density is mass over volume. It's just rearrange. I just rearranged this, so now it shows up as V equals m over d. So if I write that equation this way, V equals m over d. If I was gonna call V my y, right, and m is my x, okay, what would be my slope in this case? I can say that V equals m over d is the same thing as m times 1 over d. So I can say then that the number that I'm multiplying my x with, so this is my x and this is my y, so the number that I multiply my x with, that's going to be my slope. Okay, so my slope is going to be 1 over d, and my intercept here, well, obviously in this particular case would just have to be 0. So that's your y-intercept. All right, so let's try that now with this third equation that we have here. This is an equation you might encounter if you're going to measure what's called the absorbance of a solution. Okay, Gracie. What y would you have here and for this equation? Your variables are a and c. Okay, correct, Brian. Your y is a. And what would be our x? Okay, our two variables are a and c, so our x is just c. Okay, so a equals a, b, c. So this is my y, and I'm going to plot it versus x, and my x is going to be c. Okay, so if this is the case, if I were to plot a on the y-axis and c on the x-axis, what would be the slope of my line? AB, very good. So that's going to be my slope. And what's going to be my y-intercept? 0. Good. Okay? So you need to be able to recognize these types of equations. Okay? So anytime you can recognize an equation that's linear, that's when you have one quantity is equal to another quantity multiplied by a constant plus another constant. The equation you get is a straight line, and if you make a plot of those two things, you'll get a straight line. Now, why are we interested in straight lines? Okay, they're highly desirable because if you have a straight line, it's very easy to recognize. It's easy to recognize a straight line equation. Now, if you have curves, there are many different ways of expressing the. There are many equations that would come up as curves when you plot them. But if you have a straight line, there's only one form for the equation that you can match it with. It's going to be y equals mx plus b. Okay, so they're easy to recognize, and they also allow us to make reliable predictions, and those predictions are called interpolation or extrapolation. So for example, if I have a line, let's say that looks like this, okay, and I have this is my best fit line. Okay, so although I may have only taken these data points right here, let's say, all right, now okay, so this is x right here and this is y. So these are I've only got 1, 2, 3, 4, 5 data points. Okay, but I can make a prediction. Let's say if I were to do an experiment and my x is this much, all I have to do is draw a vertical line to my best fit line, okay, until I hit it, and then draw a horizontal line all the way to the y-axis. I can make a prediction what y is going to be if this was my x. So that is known as interpolation. Okay. Now, you'll notice that I did not go past this value of x or this value of x right here. So what if I if I said, what would happen if I were to do an experiment and my x was this much over here? Well, I can just say, okay, I'm going to draw a straight line towards this vertical line towards the best fit line, and then go horizontal across the y-axis. I can predict what my y value is going to be for this particular experiment. Since this is beyond the range of data that I have, this is what we would call extrapolation. All right, so that's the value of being able to draw a straight line. You can make reliable predictions. Now, you have to realize that if you're too far away from your data points, extrapolation tends to be less reliable. So extrapolations near your data points would be reliable, and so will interpolations, and so will interpolations. Okay? All right. Now, there are some variables that are not linearly related. So what we want to try to do is find an equation that is linear. And what we try to do is we find quantities that you can calculate from these variables that are linearly related. For example, you might encounter in this class an equation that says pressure, PV is equal to a constant. Pressure times volume equals a constant. Now, if you're going to make a plot of pressure versus volume, you're going to find that it's not going to be a straight line. It's going to be a curve, okay? So if we have data, pressure and volume data, and we want to plot a straight line, that would allow us to determine K. And the way we do that is we rearrange this into a form that we can plot as a straight line. So if you can see here, PV equals K. Let me rewrite that over here. PV equals K. If I divide both sides by volume, I have pressure equals K over volume. Well, I can rewrite that. I can say pressure equals K times 1 over volume. K over V is the same thing as K times 1 over V. And now I can identify that this, if I were to make this the data on my y-axis, and I plot 1 over volume on my x-axis, then I can see that I'm just multiplying my x by a constant. So this is going to be my slope, which we called m, right? And my y-intercept is going to be 0. So that means I would expect that if I were to plot pressure and versus 1 over V, that I'm going to get a straight line. My data is going to fall on a straight line. Okay? So let's look at a few examples of data that you can plot as a straight line. Let's say you have over here natural log of A, where A, let's say, is the concentration. So this is something you might encounter if you're doing a study of the rates of reactions. So natural log of A, okay, versus time. All right, so your actual variables that you measure would be A and time. A would be the concentration of some reactant, for example. And let's say that it depends on time according to this equation. Then you can say that if I were to use ln A as my y, okay, I'm not going to use A itself. I'm going to take the natural log of A and use that as my y value. And I'm going to use t as my time, t as my x value, time as my x value. Then I can see that y is equal to a constant, which in this case is negative k times x, which is time. So my constant here, my slope, is going to be negative k. And ln of a naught here is just another constant. A naught is a constant. You can see in this expression only a and t are variable. So this must be another constant. So I'm going to call that my y-intercept. So ln of a naught would be my y-intercept. Okay? So let's look at this next equation right here. If I were to call 1 over r my y, okay, what would my x be? Look at my variables. My variables are r and t. Let's see. Let's call in someone. Chandler? Let me see. Oh, I have to turn on your mic. Sorry. I think maybe you should just type it. Okay, good. T is my x. So it's not always going to be written as y equals mx plus b. It can be written as y equals b plus mx as in this case. So t is my x. What is my slope going to be, Chandler? Right, that's the number that you multiply t with. That's the number that you multiply x with, okay? That's your slope. And what's going to be my y-intercept? It's going to be 1 over r naught. It's not ln, okay? That's 1 over r naught. That's the reciprocal of r. 1 divided by r naught. All right, let's look at this next one. Our variables are k and t, all right? And I am going to plot something that would come out to be a straight line based on this equation right here. So everything in this equation except k and t are variables. So what should I show on my y-axis? Let's see, we've got Chandler, and who's next in the... Gracie. How about Gracie? What should I show on my y-axis? ln of k, very good. And what should I show on my x-axis? One over t, good. So this is my y. 1 over t is my x. And so what should be my slope then? The slope is the constant that is multiplied by x, delta h over r. Correct. It's negative delta h over r, okay? So it's going to be negative delta h over r. And what is going to be my y-intercept? C. Very good. Now for this last one, I'm going to leave that for you to figure out. I'll help you out a little bit. I'm going to rewrite this as 1 over p equals v naught over k plus 1 over k times delta v. All right? So that should help you out help you figure out which one is y, which one is x, which one is the intercept, and which one is the slope. All right, so I think we're okay with that. Let's move on. Okay, verifying a linear relationship. The best way to verify that the relationship between two quantities is linear is just by creating a graph, okay? And in Excel, the type of graph you create is called a scatter plot or an XY plot, all right? And so the nice thing about Excel is Excel will also determine for you the slope and the y-intercept by overlaying what's called a trend line. Okay, so this is the trend line here, for example. And that trend line is also known as the best fit line over the data points. One thing to realize about trend lines, they do not necessarily, in fact, in general, they do not go through each and every point. The best fit line is just a straight line that's as close as possible to all the points on your graph. So if you are doing a graph manually and you're doing a best fit line, you try to eyeball it so that about half of your data points are above and the other half are below your trend line, and but as close as possible to the trend line. Okay, so here is an example of a chart that Excel created. Um, Oops, what did I just do? Oh boy. Word has stopped responding. Let me redo this. Okay. Let me restore that. Let me just close that one. Open up another document. All right. Okay, where were we? Okay, so like I said, this is a chart that I created using Excel, and you'll notice that Excel gives you the equation of the straight line. In this case, uh, okay, y equals 1.8x plus 0.384. And it also shows you the y-intercept. It's 0.384, the slope is 1.8. Okay, and so these are the data points that I use to create that Excel chart. So let me show you how you can create that using Excel. Okay, and if you want, you can follow along. So I'm bringing up Excel. First thing you need to do is tabulate your data points. So it's best to just start off at the left side. So here I have time in seconds. And over here I have distance in centimeters. So I'm going to enter my time. So it's 0.50, 1.00, 1.50, 2.00, 2.50. Notice that Excel is not putting those trailing zeros in, so I can format this by highlighting it and then right click and then format cells, and then I can have Excel show 2 decimal places. So I click on number here and number of decimal places 2, and it shows it there. Okay. Okay. All right. So now I'm going to enter my distances: 1.33, 2.14, 3.08, 3.94, 4.93. Yes, I'm recording this. And yeah, I think since we have to stop at around 8:30, I might have to just go through this, and then after that you can go through it on your own, and we'll pick this up again on Friday. Okay, because I have a class at 8:35. So let me just show you how I can create the Excel spreadsheet, the Excel chart using this. So what you need to do is go to the menu, insert, okay, and you can select under charts. You can select the chart that you want to insert. Let me make this a little bigger. So insert. Okay, so here's a scatter plot. That's the kind of chart you want to make. Okay, and generally when you're doing this, you don't want to connect the dots. You never want to connect the dots when you're doing XY charts or scatter plots. So just select this one and just put markers. My computer seems to be crashing a lot. Let me close my Microsoft Office here. Microsoft Word. Oops. Oh, so it did create that chart for me. Okay. Now, Excel usually tries to figure out what you want to graph, and sometimes it doesn't get it. It doesn't get it right. So the best thing to do is, if you have a chart, okay, you need to, okay. Okay, if you click on a chart, you'll notice it shows up here, chart tools. So on the design tab, It allows you to select the actual data that you need to graph. You just want to verify that Excel is actually graphing the data you want. So you click on select data. Okay. In fact, I don't like Excel thinking for me. So usually I just remove what Excel gives me by default. And then I can add the data that I want to my chart. So I click on add right here. And then I'm going to pick my X value. So if I click on select range right here on this icon, I can pick my X values, which is going to be cells A2 through A6. I'm just going to highlight that. And then I'm going to select my Y values. I'm going to highlight the cells from B2 to B6, column B, row number 2, all the way to row number 6. And that's the data that I want graphed. Okay? So I'm going to hit OK, and so that's my chart on Excel. Now, if you're just showing one thing on your graph, you really don't need a legend. So what you need to do is click on that legend and then just hit the delete button on your keyboard. That gets rid of that, so you don't need that. All right. Now, if I want to draw the best fit line, I hover over one of the points. Okay, it will tell me that I'm hovering over a point. It will tell me what that point is. So this is 1.5 and 3.08. So that's the third point I have. Right click over that, and then you can click on add trend line. And you can select what kind of trend line you want. Generally, we want a linear trend line. And you can have it show the equation on the chart. Display the equation on the chart. And you can also display what's called R squared. The R squared tells you how good the line is, how good a linear fit is to your data. So if I click on that, there's my linear trend line. And right here, I have my equation of my line. Y equals 1.8 times x plus 0.384, which is what I showed you earlier. Okay. Now you can change how your graph appears by clicking on layout over here on the chart tools tab. Okay, so if you want to put, generally want to put titles for your x-axis and your y-axis, so you can add axis titles. Okay, so primary horizontal axis, I can put a title below it, so I can just call it x. This is time in seconds. So instead of calling it x, I'm going to call it time, since that's what it really is. Okay, and then again, layout, axis titles, vertical axis, I want it shown on the left side. That's not how I want it to show up. So let me change it. By the way, that's not what I want either. Rotated title, that's what I want. That's generally what you want to do. So I click on it, I can enter my title. So I can just type in distance in centimeter. Okay. So now my equation is really a distance versus time, so it's not really y versus x. So I can actually edit this. I can show this as distance equals 1.80 times time plus 0.384. Okay. But then you have to put units for your 1.8 and 0.384. Now 0.384 is the y-intercept, so that should have the same distance, the same unit as distance. So the unit for 0.384 is centimeters. What should be the unit for 1.8? Okay, 1.8 is the slope, right? If you want the slope, then that's delta y, change in y over change in x, rise over run. So the unit for slope is the unit for y divided by the unit for x, so the centimeters per second. In other words, what this is saying is your object was moving at 1.8 centimeters per second. It started off at time 0, when t equals 0, the distance was 0.384. It's already traveled that far at time 0. Okay, so this is a chart that you can create on Excel. Okay, and so we'll pick this up on Friday. We'll do a little bit more. In the meantime, try to recreate this graph. Are we okay on this? Okay. Now, if you look at the end of your document, at the very end, you have instructions there on how to do things in Excel using Excel 2007 or Excel 2010. Okay? So specific instructions on how to create a chart on Excel. And then we'll talk more about this next time. All right. Thank you. I'll see you tomorrow for a continuation of the lecture, and then we'll continue this graphing activity on Friday. I don't think you'll be able to take a quiz on Friday for energy. We won't be done with it. All right. Bye-bye. All right. Let's see. Stop recording. Okay.